So lesson number 7 on functions. We've looked at 6 ways that we can represent relationships between two quantities. So we can use words. We can use a table of values, we can use a set of ordered pairs, mapping, equations, and a graph. The other thing that we looked at was in a relation, we have domain, which are our input values, and we have a range, which is our output values. So as I said in the last class, we're going to look at functions. So functions are a special type of relation, kind of how thumbs are a special type of finger. So not all fingers are thumbs, but all thumbs are fingers. So not all relations are functions, but all functions are a type of relation. Your thumb is still considered a finger. It's just a special type of finger, right? Just weird. Okay. To illustrate the concept of a function, we're going to look at 2 relations which are described in words with the domain 1, 4, 9, and 16, and the range 1, 2, 3, and 4. So in the first relation, we're going to describe it as this is a multiple of this. So 1 is a multiple of 1. 4 is a multiple of 1. 1 times 4 is 4. 4 is a multiple of 2. 2 times 2 is 4. 4 is also a multiple of 4. 9 is a multiple of what? 1. And 9 is a multiple of 3. And 16 is a multiple of 1. 16 is a multiple of 2. And 16 is a multiple of 4. And then we have is the square of. So 1 is the square of 1. 4 is the square number of 2. So 9 would be the square number of 3. And 16 would be the square number of 4. So in this next part, in part B, we're going to take these arrow diagrams and we're going to create a set of ordered pairs. So if I did that for number 2, my set of ordered pairs would be 1 and 1, 4 and 2, 9 and 3, 16 and 4. What I would like you to do is I would like you to write down all the ordered pairs for the first relation. Okay, so if I write down my set of ordered pairs, I have 1 and 1, and then I have 4 and 1, 4 and 2, and 4 and 4. I have 9 and 1, and 9 and 3, 16 and 1, 16 and 2, and 16 and 4. Correct? Okay? So now what we're going to do is we're going to take these ordered pairs and we're going to plot them on the grid. So again, I'm going to pick B. So if I plot these 1 and 1, 4 and 2, 9 and 3, 16 and 4. So I want you to do the same thing with the first graph. Plot those points. So we have 1 and 1, 1 and 4, 4 and 1, 4 and 2, 4 and 4, 9 and 1, 9 and 3, 16 and 1, 16 and 2, and 16 and 3. That makes sense so far? Okay, so now let's look on the next page. By definition, a function is a special type of relation where every input relates to only one output. So each element of the domain relates to exactly one element of the range. So if I look at the previous page and we look at this exploration, if the definition of a function is that one element of the domain maps to one element of the range, is this a function? No. How do I know? First of all, looking at this arrow diagram, how do I know that this is not a function? I'm branching off to more than one. Is this a function? Yeah, because I only have one arrow moving along. So one arrow from 16 going someplace, whereas here I have 3. This is how I could tell, using an arrow diagram, that this is not a function. So let's find a way to put that in words. Explain how we can determine which relation is a function by looking at the following. So if I look at an arrow diagram, how do I know that I have a function? Because there is only one arrow from each input. Does that make sense? And maybe in brackets we can put domain so that we remember that domain is input. Okay, so let's go back and look at the ordered pairs. So we know this side was not a function and this side was. Looking at the ordered pairs, how can I look at a set of ordered pairs and determine whether or not I have a function or not a function?
If the domain is there,
so if I have multiple times where I have the same x coordinate, right? So let's try to find that in words. So from ordered pairs, how would we write that? How do I know I have a function? What am I looking at in particular? I'm looking at which in an ordered pair? The x coordinate. So if I said that each x coordinate corresponds to only one y coordinate. That would be a function. So in my first, or on the left-hand side, I had 4 and 1, 4 and 2, and 4 and 4. Because the x-coordinate could go to 1, or 2, or 4 for a y-coordinate, it's no longer a function. Because I basically used the x-coordinate more than once. Look at the graphs. If I look at the graphs, how can I tell the difference between no function and function? Yeah, if I have more than one point going up from the x-axis. Okay? So, how can I tell if it's a function? I could say if each point on the horizontal axis has only one point on the vertical. So graphically, if each point on the horizontal has only one point on the vertical, does that mean graph A, each point on the horizontal has only one point on the vertical? Would this be a function? Where do I have 2 points on the vertical from the horizontal? See, if I look right here, yes, I have the same vertical, but they have different horizontal points. So I could have the same vertical outcomes, but I have to have different horizontal ones. So are my horizontals always different?
Yes, there is a function.
So is this a one-to-one? Which would mean that this is a function. Is B a function? Is C a function? Why not? Well, if I have an input of 3, how many outputs do I have? I have 2 outputs. I can't have 2 outputs. What about D? Is D a function? No. Same thing. An input of 5 gives me 2 possible outputs. Okay, so let's look at some of the other ways that I can help determine the function in the function. So it says classify each of the following statements as true or false for A, B, C, and D. Well, we've kind of done this one. For each input, there's only 1 output. That was true in the first 2 and false in the last 2. For each output value, there's only 1 input. So this time I'm looking at the verticals. This one's false. Because if I have an output of 5, there was 2 possible inputs. So that's false. Is this one true? Yes, because an output of 5 only gave me 1 input. An output of 2, only 1 input. So this one's true. What about C? If I have an input of 5, if I have an output of 5, how many inputs did I have? 2. So this would be false. Okay? And in D, if I have an output of 1, how many inputs did I have? 1. So this one would be true. And then the bottom line is we had to identify whether or not the relation is a function. And we've already done that. True, true, false, false. So from here, the part that matches up is the input. This is what matched up to whether or not it was a function, is what my inputs did. It doesn't matter with my outputs. I can have the same output as long as the inputs are different. So I can have an output of 5 as long as my one input was different from the other input. So from graph C, it says write 2 ordered pairs that show that the relation is not a function. So if I look at graph C, what points could I use to show that this is not a function? So pick an input. Okay. Do I have a nice point here to figure out what that point is?
No.
Is there a point on the graph that does work out nicely?
-1.
-4 works out pretty not bad. Okay, so what's the coordinate right here? -1 and 2. And what's the point up here? -1 and 8. So that's on the top of the next page. -1 and 2, and -1 and 8. It says, draw a line joining these points. So if we draw a line joining these points, and we'll change the color of the line so that it stands out. There's my line joining those 2 points. Okay? So if I look at graph D, let's find 2 points on this graph that prove it's not a function. So can you find 2 nice points on the graph where I have the same x value?
2.
2 and what?
Or no, 1.
1 and 1 and 1?
And 1 negative.
And 1 and negative 1. Okay? So we'll put that on the next page. 1 and 1, 1 and negative 1. And I could have taken like 4 and negative 2 and 4 and positive 2. So again, if I join these points with a line, we'll do it this way. What kind of a line did I draw? A straight line, and it went vertically. Okay. We call this the vertical line test. If I have a graph and I draw a vertical line, oops, and do that. We'll make this nice and orange. The vertical line test says if I take a vertical line and I slide it through a graph, if it hits the graph in 2 places, it's not a function. At any point. So right here, it only hit the graph in 1 spot. But because when I move it over, it hits it in 2, it basically makes the whole graph not a function. That's the vertical line test. Oh, and the answer to question D, on graphs A and B, if I draw a series of vertical lines, do they intersect the graph at more than 1 point? No. So the vertical line test is the test that can be used on the graph of a relation to determine whether or not it's a function. If every vertical line drawn on the domain intersects with the graph exactly once, then it is a function. If it intersects the graph more than once, then it is not a function. So that's the easiest way to tell if a graph is a function. If a set of ordered pairs is a function, or if it's not, because it's probably easier to prove that it's not a function, I look for common inputs. And then for an arrow diagram, I look for multiple arrows leaving the same input. So we're going to look at class example number 3, and we're going to see whether or not these, I think there's 7 of them, whether or not these are functions or not functions. So is A function?
No.
Look at the x-coordinates.
It could, yeah.
Do I have the same x-coordinate?
5 and negative 5 still intersect. 6
These are not the same. 5 and negative 5 are not the same.
6
6 and 6 are. So because I have 2 inputs, this is not a function. Okay, look at the x-coordinates for B. Do I have the same x input? No. So is this a function? Yes. It's possible to have the same output. I can have them both going to 3. Has an output. Okay. Is C a function?
Yeah.
And why is it a function? Because I only have 1 arrow leaving each. These are are my input. And I look, the arrow, I only have one arrow leaving element C. I only have one arrow leaving element B. Even though they're both going to Q, there's only one of them. So this is a function. In D, I have a graph. So if I have a graph, I'm going to draw a straight line. And I'm going to use my straight line. And I'm going to use my straight line for my vertical line test. And I'm going to see, does it intersect 2 points at the same time? Yes. So this is not a function. And the reason why is it fails the vertical line test, which you can abbreviate as a VLT. Just don't gamble on it. The relation connecting the provinces and territories with their capital cities. So what's the input? What am I putting in? The province or territory, okay? What's the output? The capital city. So is this a one-to-one? Does a province have more than one capital city? No. So is this a function? Yes. Okay, so try to do F and G. Okay. So we said that this would be a function because in each province there is only one capital city. Ontario does not count as two because Ottawa is the capital of the country, not the province. I've had that used on me before. F, I have a graph. Does the graph pass the vertical line test?
Yes.
Yes. So is this a function? Yes. Okay. And in G, does it pass the vertical line test? No, it fails it. It doesn't fail it all the way across, but it just has to fail it once for it no longer to be a function. So this is not a function. Okay. A function as mapping. A function from a set D, the domain, to a set R, which is called the range, is a relation in which each element of D is related to exactly one element of R. So the way that we can write it is we can use notation of function F. So we call the function F. We could call the function G or H or P, but F is commonly used because F stands for function. And we can say the function X mapping to Y. So if we go back to the first page where we had that mapping of 1 to 1, like those ones, if we went back and we completed this, 1 would map to 1, 4 maps to 2, 9 mapped to
3.
and 16 mapped to
4.
Oops, I didn't put that the right way.
4 maps.
16 mapped to 4. So question 4 says consider the function f where x maps to 3x plus 1. So an input of x gives me an output of 3x plus 1. And then I have the following domain, -1, 0, 1, and 2. So if I input -1 into this output, what would I get? -2. 3 times -1 plus 1. If I input 0, what do I get? 1. 3 times 0 plus 1. If I input 1, I get 4. If I input 2, 7. So what are the elements of the range? Say that again?
-2, 1, 4, and 7.
The range are my output values. So now if we show this function as an arrow diagram, a set of ordered pairs, and a Cartesian graph. So as an arrow diagram, I need 2 ovals. So there's my arrow diagram. The first oval has my inputs. What were my input values?
-1, 0, 1, 2.
And then I map them. -1 maps to,
-2.
0 maps to,
1,
1 maps to,
4.
and 2 to 7. There's my arrow diagram. If I had a set of ordered pairs, what would they be?
-1 and 2.
Pardon? 0 and 1. And then if I graph this, I'd have -1, 0, 1, and 2. And then I need to be, so there's -2. 1, 2, 3, 4, 5. I need that smaller. Go up to 7. 1, 2, 3, 4, 5, 6, 7. So -1 and 2 would put a point down here. Zero and 1. 1 and 4. And 2 and 7. So if you notice in this graph, the way that we've labeled the domain was my x-axis, the range was my y-axis, but I relabeled it as 3x plus 1. Okay? In the next lesson, we will label it a little bit differently. Your questions, 1, 3, and 5, 7, and then 9 to 12. And you guys have 40 minutes.